Our next presentation actually is a collaborative project between FIU, OU, and UNR, Risk and Resilience of Bridges. Dr. Islam Mantawy will, I believe, will start the presentation, and Dr. Musharraf Zaman and Dr. Mohamed Moustafa will take on their segments in the presentation. And Dr. Mantawy.
So thank you everyone for staying with us today for the Research Day presentation. So this presentation features project entitled Risk and Resilience of Bridges Toward Development of Hazard-Based Assessment Framework, Research Need and Benefit from ABC. With me today, Dr. Musharraf Zaman from University of Oklahoma and Dr. Mohamed Moustafa, University of Nevada, Reno. And also we have Dr. Edward Coakley from University of Oklahoma as a co-PI, and we need to acknowledge the students Paul and Mohamed Ibrahim from University of Nevada, Reno, Paul from University of Oklahoma. So just a quick introduction here on resilience definition and different assessment metrics. So resilience is actually defined in so many different ways and so many different references. So from National Research Council and NIST, its ability to prepare and plan for, absorb, recover from, and more successfully adapt to an actual or potential adverse event. And there is a cloud image here that showed from literature how often those keywords are mentioned. So you can see in the screen the resilience, community planning, anticipation, bounce back, social capital, etc. With this, moving forward, there is also many different assessment metric. The most famous one is called 4R methodology, which is developed at University at Buffalo. So in the horizontal axis, you can see the time, and time 0 is time of the event. Time 1 is the time where it's anticipated to recover. The vertical axis is functionality. This can be for any system, but if we focus on a bridge, for example, we can have normal functionality and an event. The event can be hurricane, can be seismic event, etc., or flooding. And due to those events, you have drop in functionality. So we have the pre-hazard functionality, we have functionality loss, and the residual functionality called robustness. And the objective is to restore either 100% or percentage of the pre-hazard functionality. In this case, we mentioned 100% recovery. This happens over time, which defined as rapidity, or downtime that include a time needed for like overcoming the impeding factors such as inspection, crews, and the crew of inspections, and also the office work for processing the evaluation and the actual repair time. This area is called resilience in a loss indicator, which we target to have a smaller area in this case. And this time is, as I mentioned, end of repair. And there is also other metric called redundancy and resourcefulness. Next slide, I will show the definitions of robustness, rapidity, redundancy, and resourcefulness. So robustness is the ability of a given system to withdraw or resist a given hazard with minimum or no functionality loss. Rapidity, as I mentioned, recovery time needed for a given system to bounce back to pre-hazard functionality. Redundancy is an inherent component that can keep the system functional even after the loss of some element. And resourcefulness is the ability to mobilize resources to recover from hazards. This project actually is trying also to extend 4R to 5R, considering regional, societal impact, and economic. Role of ABC, or accelerated upgrade or accelerated repair. So in this chart, if we assume accelerated upgrade, we would be able to increase the pre-hazard functionality. And if you assume the same effect of the hazard, you will actually have the same functionality loss, but you will inherently increase robustness. If you assume the same time needed for overcoming the impeding factor and same rate of repair, you will successfully decrease the area of the resilience triangle or its resilience shape. So accelerated repair before the event can actually increase robustness and reduce rigidity, which is beneficial. Accelerated repair can actually, if you assume the same system, but you have an accelerated repair methods that can actually increase the slope of the repair or rate of repair, which will actually reduce rigidity, which is desired. So the overarching goals of this project is actually to document the current state of practice related to assessment of risk and resiliency for bridges nationally and internationally, not only bridges, but also other application for buildings, so we learn from it. Make some synthesis of state of practice related to assessment of risk or resiliency for other structures I mentioned for man-made hazard, since there is a lot of existing tools for buildings, for example. Also conducting a target online survey with state DOT and other stakeholders to evaluate the practice and perception of existing bridge performance tool. Develop holistic and comprehensive resilience and risk assessment framework for existing and new bridges with emphasis on accelerated construction benefit. And based on different hazards, we will be selecting one hazard, which is seismic, to develop a specific resilience framework for seismic hazard, as I mentioned, as an example of natural hazard. With that, I will give the mic to Dr. Moustafa to brief us on the first task and second task related to literature review and synthesis of existing hazard and risk assessment tools. Dr. Moustafa,
thanks, Dr. Mantawy. So, at UNR, we will be leading, the tasks related to the documentation and the synthesis of the current, state of practice. And as, Islam was just saying, there is a lot of work that was done in other, applications similar to buildings and infrastructure systems in general under different hazards, not necessarily seismic, but even under different hazards. So our goal in this task is to try to collect this information and to try to provide, a summary and a synthesis of what exists. So we will be documenting, the existing guidelines and protocols used by state and federal DOTs and cities for bridges specifically. That's our starting point to see where do these, bridge owners and others stand in terms of the latest design protocols that they use. Is the resilience part of this? And you'll hear about this more, when from Dr. Zaman when he talks about the survey. So this is, just to get an understanding where people stand. What are the existing, knowledge out there? There is a lot of work that was done in general on reinforced concrete structures or steel structures, regardless of the application, whether you use it in a bridge or in a building. So that's what we are looking at. So the references in this case are not only articles or reports, as you would typically do in a literature review or in a synthesis, but we are also looking at standards, codes, guidelines, tools, or toolkits that are, currently used by state DOTs as well. So can we go to the next slide? So we started by looking into, or trying to categorize, the information out there. So we started with about 165 sources or resources, and with this, the ones that we believe are the key, documents in this area, and we start classifying them into categories just to see how we can make the best out of them. So we came up with 15 categories that you can see here, and I will show samples in the next few slides. But you can see that some areas, have a lot of work that has been done already. Like if you look at category E, for example, which is the performance-based design, there is a lot of resources out there. There is a lot of, preliminary or non-mandated, I would say, frameworks that can be readily used now. Although none of the codes, are mandating performance-based design yet, but still the comprehensive documents are out there. So there is a lot of not only research papers. Again, let me stress on this: it's not only research papers that we are looking at here, but we are looking at existing design guidance and tools that has been already used by design firms or infrastructure owners. So these are some of the categories. If so, I will just pick some examples from the next few slides and show you in general what would be each of these categories would entail. So if you can go to the next slide. The ABC technology, for example, this has to be related to the ABC. So regardless of, you are doing resilient-based design or displacement-based design or force-based design. This is conventional bridge versus ABC. So we wanted to first know what are the latest on the ABC toolkits out there for the design, and see how this can be tied eventually to the resilient-based design. If we focus on general bridges aside from ABC and we look at the bridge resiliency in general, there is a lot of work that was done to explore or develop fragility curves for different components of bridges, original columns, retrofitted columns, like the functionality of the bridge, and so on. There are frameworks that were specific for bridges, not only for buildings, but for or not specifically for buildings, but rather general or specifically for bridges. And these included different hazards. So we have seen some work that was done on earthquakes, tsunami hazards. Professor Bucket here at UNAR has done a lot of work on tsunamis and their effect on the bridge design, and so on. Next slide. Displacement-based design. And this is the origin, I would say the origin of performance-based design, where people start switching from force to displacement-based design, or use displacement-based design to complement force-based design. We found that displacement-based design is more appropriate for a lot of design categories like the seismic design specifically, or retrofitting, and this what emerged later to resilient-based design. So we are trying to find this connection, how people emerged from force-based design to displacement-based design, and how displacement-based design emerged to resilient-based design or performance-based design first. So we are trying to find these connections, and again we focus mostly on seismic because many of these design frameworks, when they were developed only for seismic, but then later on they start being used for other so performance-based design, that's originally was developed for earthquake engineering, but you can see now there is a lot of work on performance-based wind engineering. That's even part of ASE committees now. There is work on flooding and hurricanes for performance-based design as well. So we try to create and establish these connections and see how we can benefit from history and how can this be reflected in the bridge world. Loss estimation is a big deal when it comes to the resiliency, and how to calculate the cost of structural retrofitting, the earthquake, again, losses, since this is most of the work that was done in the seismic area, estimation of the recovery time and time loss, because these translate into, or participate into the resilient assessment, as you have seen also from the previous slides that Islam showed. And we can keep going, please. Next slide. How to optimize the design resiliency at the community scale. So these are all different categories. I don't have to go through each of these line by line, but in general these are some of the groups that we are looking at. If we can go to the next slide for the last groups. Standards and code and recommendation, and this is the part that I mentioned a couple minutes ago, is that we are not only doing state of the art here in terms of research, but we are doing state of practice as well. And we are trying to look at the standards and the current existing design guides and recommendation for multi-hazard design, for seismic rehabilitation, specifically for bridges. And a good example for bridges is the very recent NCHRP report that came, I think, a year or so ago on performance-based bridge engineering. And this has a new, design tools for bridges. So this could be a very good starting point, again, for resilient-based design eventually. So we are not looking only at the state of the art, but we are looking at the state of practice as well. Seismic design has been, the key part of the literature, again, just naturally, because many of these design frameworks, were applied for seismic first before it starts migrating to other hazards. So we are focusing on also on seismic for general structures, and eventually we will look at a critical infrastructure at the system level so that we have a complete picture. So in summary, what we are trying to do, we can skip this slide and we can just go to the next one. So what we are trying to do basically after we, and we are almost done with the review of all these 160 or 170 different, pieces of information that we have. And the way that we are going to present this, aside from the categorization that you just saw, we will have a final report that will include all the, the tasks of this project. We will focus on 2 chapters basically. We decided to provide one chapter that is general, independent from bridges, and this is what will provide the history. We will see how the background on structural design in general. You see here RC in the title. This is a typo. It's not necessarily reinforced concrete structures. This is just general structures. So the RC here should be replaced with the word general structures. So we will start in this chapter summarizing the history of the structural design, force-based design, how it emerged to displacement-based design, and then how it emerged to performance-based design, and create these connections so that when we start talking about resilient-based design, we can see again what's the natural progression of these design frameworks and what can be imported from existing design guidance and what need to be developed. So that will be a general chapter that provide, or talks more about the history of the design. Then we will have a specific chapter, chapter 3, that will focus specifically on the bridge design frameworks. Whether, we try to mimic what we have done or what we are currently doing in chapter 2 and also track the history of the design of bridges, or we focus mostly on performance-based design of bridges and just get to the, the state of the art directly, and use this, NCHRP and new ASH2 guidelines that were just published last year, as I said, for performance-based seismic design of bridges. We will focus on this as our starting point. We will see how to combine what was emerging for bridges in general with what is emerging for ABC in terms of the design guidance for the ABC under extreme events, and then develop, combine the two to rethink, or basically the design guidance, how to make them ABC, sensitive or sensible, and how to use what's needed for the connections specifically. And eventually, we will provide any information that we would see as well. And this is not going to be practiced now. It will be state of the art in terms of research, because I haven't seen personally any resilient-based design framework for bridges that has been emerged to be applicable at the state level or at the city level. It's all at the research level yet. So that's how we will conclude this chapter. So hopefully by the end of this project, these two chapters, along with the other ones, will provide, as I said, and as Islam said earlier, an overview of where do we stand and where should we be going from here. So thanks for listening.
Good morning and good afternoon, everyone. I think, as you know, this is a collaborative project in which the University of Oklahoma is responsible for conducting a survey of the state DOTs and some selected, cities. So I think developing the survey actually took some time, because we wanted actually to make sure that the survey does not take too much time. So I think our goal was to actually keep the survey within 30 minutes. And I think and it also took some time, to get approval from the IRB before we could distribute the survey. So the idea was to actually, document, through the survey, the current practice on the assessment of risk and resilience of bridges, to natural hazards and man-made hazards. So there are total 15 questions, and in order to keep the survey to a limited time, we have provided multiple options. So as much as possible, these questions are multiple questions. So there are 15 questions altogether. The first question, I think I'm not going to go over. If we go to the next one, so I am going to the next one, please. So I think so these questions actually, the first one, as you can see here, is regarding the perception of ABC. So there also, I think we have given them, some options like, the safety and mobility, durability, delivery time, environmental impact, cost, and social. So if they could, select this in terms of, choices like significantly positive or only positive, no impact, negative, or significantly negative. By providing, this type of option, we thought that it will encourage the participants to actually, take the survey, and we hope to have, good outcome, good participation across the country. One thing I just want to point out is that our DOT in Oklahoma, the Bridge Division is helping us to distribute the survey to the state DOTs, and also they are helping us to distribute it to ASH2. I think that is helpful. Question 2, I think this relates to definition of resilience. So I think there are different definitions. So we are asking them to sort of see which definition they use. And question 3, it relates to type of hazards. So there are, we have given more I am, if you scroll down, I think that may or may not. But anyway, I think we have given them, choices in terms of the type of hazards. Coastal surge, earthquake, explosion, fire, flood, hurricanes, impact load, and so on and so forth. So they could actually, the person responding to the survey, could, and again we have given them a range. Is it important? From not important to very important type of, the scale. Then question 4 starts from the tools and software that are used by the agencies. So there again, we have given them choices like, not used, or used and mostly used. So we have given them, hazard image, recast, finite element modeling, ECNet, and so on. So we have given, these choices to, to them, and say that, okay, your agency, does your agency use this or mostly use this, in that type of a scale. That's what is given. Question 5, I'm not going to go over all the questions, but just to give you sort of an overview of what type of questions we're asking. And as I am is showing there, so I think it is fairly a friendly way of actually answering to this survey. So question 5 relates to hazard maps. So again, we have given them the choices. Do they use geological survey maps or FEMA maps or National Weather Services or Hurricane Center in map? And question 6 relates to hazard prediction. So I think we just want to know, what are the most important to least important. So there are number of choices. Is it budgetary issues, resource including human resource issues, or lack of damage prediction tools. So again, and then for each question, we have given them choices to add other things that we may or may not have included. So they could add actually, their own, hazard prediction tools and rank them accordingly. Question 7 relates to resilience. So again, we're saying that does your agency quantify the structural resilience of bridges? And if yes, then we have given them choice. Then which method do you use in quantifying resilience? So that's question 7. And then question 8 relates to, so that if we have a damage, then how does your agency prioritize the recovery of affected bridges? So again, that's most important to least important, and we have given them choices, in terms of prioritizing the recovery of affected bridges. So you can see this, this is kind of how we led this survey. So question, I'm skipping question 9. Question 10 is functional loss. So we're telling them that if they could select up to 3 most common approaches for using, for determining the functionality loss. So we have given them a list, and out of that, they will select the top 3. The way this platform that we're using is fairly easy to actually do it, for the participant. So that was question 10. Question 11 is related to redundancy. So again, I think we're giving them some choices. So we're saying that how is redundancy incorporated in their design? So and there are choices. So they could actually select based on what is practiced within the agency. So question 12 actually relates to how do they decide that whether a bridge should be replaced or repaired? In addition to cost, what other factors do they look into, like the time, for example, closure time, traffic safety, social impact. So those are also important, as you have seen, that's one of the benefits of ABC, that it is not only cost, but it definitely is important to safety of the traveling people and safety of the workers. Question 13 relates to the time. So that's the and we have given them sort of a range as to what their agency considered this the inspection time following a hazard, either natural or man-made. Question 14 relates to repair, I think similar, and finally question 15 relates to the emerging technologies. So there again we have given them is your agency using these emerging technologies like artificial intelligence, robotics for inspection, or adaptive construction, machine learning, smart materials and structural health monitoring. So we have distributed this survey to the state duties. We're in the process of distributing it to and to ASTO, and we're in the process of distributing it to the FHWA divisional offices. In terms of cities, I think we may have to do selectively, like maybe Miami, like for example, because of FIU, and then perhaps Oklahoma City and Nevada, Reno, or something like that. But that's something we still need to work out. That's what I have to say, and we look forward to receiving good feedback and then summarizing them in the report that we'll be preparing together. Thank you.
Thank you, Dr. Zaman. Dr. Mantawy, do you have anything to add to the?
So we do have some slides, but we have the progress report posted online for the rest of the presentation if you are interested to know more. Basically talking about different hazard and sequence of hazard and as the proposed framework. So we are waiting for the survey result and literature, synthesizing the literature to finalize that. So with that, I will conclude our presentation, and thank you for listening to us. Thank you.
Thank you very much, Drs. Mantawy, Zaman, and Dr. Moustafa. Very good project. It's a lot of work done, so please, to know more details, to go to our website and find the project. Very easy to navigate and get the details out of it. If there is a question, we will forward to you later. Thank you again.